after work, we need to talk about different types of energy. And these different types of energy are potential, kinetic, and mechanical. And then also we're going to just talk about power briefly to give you some basics. Again, more specific videos about solving problems will be included later. So the first type of potential energy is called gravitational potential energy, and it's based entirely on position, or your height. So the equation for this is your mass times g of the planet you are on, so normally on Earth, 9.8 meters per second squared, and then your height in meters above your 0 point, right? So mgh is how we talk about potential energy. So a couple of different situations. Let's take a look at this ball. It's on a staircase. And as the ball comes down, its potential energy is going to increase or decrease, right? Its height's greatest at 50. Here, let's say it's 40. Here, let's say it's 30. Here, it's 20. At D, it's 10. And at the bottom, our potential energy is 0. Our change of energy as we go down the steps is 50 to 0. Let's say the same ball at 50 joules of energy is on a slope, and we let it go right down the slope. It's going to go from 50 to 0. The same amount of energy potentially is lost. It goes from 50 to 0. Happens a lot faster as you go down the slope than if you go stair to stair to stair to stair, but in fact it's still the same change in energy. What about the same ball if it drops straight down? At the very bottom it's still going to be 0 because our height is 0. So therefore our loss in potential energy is still 50 joules. So potential energy has nothing to do with how fast the whole thing happens. It's based on how much where your height is, okay? And how you get from point A to point B. If you go from 50 to 0, you go down the stairs, you could slide down or you could drop down. It's still the same. So potential energy, same as height. If you're on a swing set, your potential energy is highest when you are farthest off the ground. In this case, compare those two. This guy here is a little bit farther off the ground, so he has more potential energy. So this is most potential energy. This is second most, and lastly, this is third most. But potential energy is based on height. Okay, keep that in mind. Gravitational potential energy is based on height. I think I said it enough. Elastic potential energy is based on kind of spring. So spring force is your spring constant times x, the distance that the spring is compressed. To find the energy in the spring, it's a derivative, right? So it's 1/2 your spring constant times your distance you're compressed squared. So potential energy in a spring is 1/2 kx squared. So an example would be a spring-loaded gun. When you compress the spring, the distance you compress the spring is your x. K is a constant. It just tells you it's in newtons per meter, and what happens is then you can use that information to find your potential energy. Just because you multiply that by meters squared, 1 meters cancels, newtons times meters is equal to a joule. Okay, there's the math for it. But just understand that potential energy is 1/2 kx squared of a spring, and x. K is a constant that you have to know or have to solve for, and x is the distance the spring is compressed. Kinetic energy we've talked about before when we talked about momentum, but kinetic energy is 1/2 mass times velocity squared, where m is mass, v is speed of the object. Pretty straightforward equation. And again, we've talked about this already. Now, mechanical energy, and there's a lot to talk about here, so I'm going to do these point by point. Point 1, the energy acquired by the objects upon which work is done is known as mechanical energy. So energy, all right, that is gained when work is done to an object is mechanical energy. It's energy that's possessed by an object due to its motion or due to its position. So it could be its kinetic energy or it could be its potential energy. Mechanical energy can be kinetic or potential, all right? And that's important to understand. So any object that possesses mechanical energy, and this is big, is able to do work. So mechanical energy is the energy to do work, is another name for it. So an example here is you got the ball here, right, of the demo machine, and it has potential energy at the very top. As it moves down, this energy becomes kinetic because it starts to move faster. So now this will have kinetic and potential energy together. That energy together is going to do the work that's needed to destroy this building. So potential and kinetic energy together do work. Mechanical energy is the ability to do work. Let's look at a couple of other examples. You've got the hammer, right? And the hammer is going to have some kinetic energy as you swing it. It is going to do work on the nail because it's going to apply a force to the nail to move it a distance, right? It's going to move that, displace the nail, and it's going to go in the same direction. So work, remember, is force times distance. Bowling. The ball has kinetic energy due to its motion. The pins are stationary. Once the ball hits the pins, it applies a force that moves the pins a distance, right? And if we move the pins a distance, we are doing work. So mechanical energy, in this case kinetic, on both these in both these situations, the kinetic energy of the objects is doing work on the stationary objects that it comes in contact with. Now, total mechanical energy is potential plus kinetic. Okay? If we look at any situation, we could write down potential energy of gravity, potential energy spring, plus kinetic energy will equal total mechanical energy. Do you need to have all of these together? No, you might have one, you might have all three, depending on the situation. But at the end of the day, any one of these by itself or added to the others will make total mechanical energy. So here we got a ski jumper. At the very top, not moving, has a potential energy of 50,000 joules. As the object goes down, or as the skier goes down, gains some speed, so its kinetic energy increases, but loses height, so its potential energy decreases. But our two energies together, total mechanical energy, will stay the same. It'll still be 50,000. At 30 meters, we have a kinetic energy of 35,000, a potential energy of 15. But again, added together, still equals our initial mechanical energy of 50,000. When the ski jumper's in the air, 60 meters above the ground, you have a kinetic energy of 20 and a potential energy of 30, but we know those two added together will still equal 50. And then at the very bottom, when the skier lands, potential energy is 0 because you're on the ground, so kinetic energy has to be 50,000 joules. But throughout the whole process, total mechanical energy is conserved. Okay? Is conserved. And lastly, there's power. Power is how fast we do work. So it's work divided by time. We use the unit watt to describe power. And another term that comes up is horsepower. And really, 1 horsepower is equal to 750 watts. So now here's how it all works. Power is work divided by time. Work is force times displacement. So force times displacement over time is also power. If we factor out force and take force times displacement over time, we also have power. So another way to talk about power is force times velocity. So there's actually 2 equations for power. The standard work divided by time, and then also force times velocity, which you might find to be easier depending on the problems that you see. Again, problems over all of these types of situations will be coming on a different video. This is just some background information with units, etc., and equations. If you have any questions, let me know.